Welcome to the fourth part of the video series on ABG. So far we have seen what is ABG, how our body maintains a normal acid-base balance, and how we can read a report of ABG and diagnose some basic disorders, and what is anion gap, what is compensation, and how to diagnose some mixed disorders. Today we will be specifically focusing on a measurement called delta ratio and see how it is important to diagnose some coexisting metabolic disorders with high anion gap metabolic acidosis. To start, what is high anion gap metabolic acidosis? We have seen that in high anion gap metabolic acidosis, some unmeasured anions were increasing, like lactic acids and keto acids, etc. And let's say that HA is that acid, so it will disintegrate into H plus and A minus. So this extra acid has to be neutralized by our body's buffer, like bicarbonate buffer. Bicarbonate plus H plus will H2CO3, then H2O plus CO2 excreted by lungs. So see that a anion, unmeasured anion, is now present in the body, and a bicarbonate ion which was previously present in the body is now not present in the body. So a bicarbonate ion decreases in exchange of a increase in this A minus anion. So to look in scale, that let's say this is the sodium, amount of sodium ions, this is potassium, this is unmeasured cations, and it is unmeasured anions, it is bicarbonates, and it is chlorides. So this is the normal anion gap in that person, the sodium minus chloride plus bicarbonate. Now if he undergoes a metabolic high anion gap metabolic acidosis, what will happen? The unmeasured anions will increase. The unmeasured anions were like this, so it will increase. Let's say they increase this much amount, so it will be now their unmeasured anions. The bicarbonate will decrease this much only, so the bicarbonate will be like here, HCO3 minus, and the chloride will be similar. So now what is the anion gap? This amount of anion gap is there already, and now the extra amount of anion gap which has been added is this amount. So this amount of anion gap is contributed by the unmeasured anions. So see, the yellow amount is consequently the increase in amount of unmeasured anion, the decrease in bicarbonate anion, and also the increase in bicarbonate increase in anion gap. So we can say that delta unmeasured anion is equal to delta bicarbonate ion is equal to delta anion gap. As unmeasured anion is not measured, so let's remove it from the equation. So we can say that delta anion gap by delta bicarbonate ion is equal to 1. So this ratio we are calling the delta ratio. So this is not always 1, because what is happening, that we are assuming that every unmeasured every pathological acid is being neutralized by the bicarbonate buffer, but bicarbonate buffer is not the single buffer in our body. There are many other buffers, like in bones and etc. So other buffers will also neutralize some of this acid. So the total decrease in bicarbonate ion will be less than the increase in this unmeasured anion or this anion gap. So if the bicarbonate, delta bicarbonate is less than the delta anion gap, so it will be more than 1, the ratio will be more than 1. So we have calculated this ratio and we have seen that in ketoacidosis like diabetic, alcoholic or starvation, it is 0.8 to 1.2, and in lactic acidosis it is 1 to 2. So it starts as 1 and then as time goes by it increases. Also this delta ratio depends on GFR, because if GFR is decreased, so renal clearance is less, so there will be more built up of various unmeasured anions that are basically normally excreted by kidney in our blood. They will increase, so the anion gap will increase. So if the anion gap is increasing, the delta ratio will also increase in decreasing GFR. So how to calculate the delta ratio? As we have seen, it is delta anion gap by delta bicarbonate. So what I mean by delta, that increase in anion gap, the anion gap is increasing. So how much it is increasing? The what I am measuring, the measured anion gap minus the normal anion gap, what it should be, like 12, divided by the decrease in bicarbonate. The normal bicarbonate is, let's say, 24 minus the measured bicarbonate. So in this fashion we calculate the delta ratio. So let's there is another thing known as delta gap, which is basically delta anion gap minus delta bicarbonate. This is not a very reliable measurement. It has more margins of error, so it is not normally used. Let's look at some examples. Here in this question we have seen a patient of type 1 diabetes mellitus with vomiting, abdominal pain and fever. Whenever I see a type 1 DM and abdominal pain and vomiting, the only thing that should come to mind is, yes, it is DKA, diabetic ketoacidosis. So let's look at the ABG report. pH is 7.3, which is less, that means acidosis. Carbon dioxide is also less than 35, which means same direction change, metabolic acidosis. Now the next step is calculating the compensation. What is the compensation in metabolic acidosis? The level of PaCO2 is 1.5 into bicarbonate is here 15 plus 8, 15 এর আধা হচ্ছে 7, 15, 16, 17, 18, 19, 20, 21, 22, 22.5 plus 8, which is 30.5. So PaCO2 is 30. So it is nearly equal. So we can say this metabolic acidosis is adequately compensated. Now, as it is a metabolic acidosis, we should calculate the anion gap. Anion gap is 140 minus chloride is 95 minus bicarbonate is 15. So 90, 10, 100, 5, 5, 10, 110, 140 minus 110 is 30. So the anion gap is 30. So it is high. So it is a high anion gap metabolic acidosis with compensation. Now we are calculating the delta ratio. The delta ratio is, as we have known, that 30 is the anion gap minus normal anion gap is 12 by 24 minus the bicarbonate here is 15 is 18 by 9, which is 2. So as it is we have seen from the clinical scenario a diabetic ketoacidosis. We have seen that diabetic ketoacidosis basically the delta ratio should be between 0.8 to 1.2, but it is 2, so the delta ratio is more than expected. So if the delta ratio is more, what that means? That means that the bicarbonate, delta bicarbonate is less. What is the delta bicarbonate? 24 minus by this, so it is less means the bicarbonate is more. So if the bicarbonate is more than expected, that means that is the secondary disorder is a metabolic disorder, and bicarbonate is a alkali, so the bicarbonate is increasing, that means a metabolic alkalosis. So a metabolic alkalosis with a high anion gap metabolic acidosis, this is the mixed disorder present in here. What can be the metabolic alkalosis? Maybe because of just vomiting out some HCLs from gastrointestinal loss, that can cause metabolic alkalosis. Okay, so in the next example we have seen an alcoholic found in roadside unconscious with vomit all around, so a classical alcoholic case. So there the pH is 7.2, which is less, which means it is acidosis. PaCO2 is 68, which is more than 45, which means it is a respiratory disorder, respiratory acidosis, and a alcoholic of vomiting, it is a acute disorder, so acute respiratory acidosis. In a case of acute respiratory acidosis, the compensation formula of bicarbonate is 24 plus the difference between 68 PaCO2 minus 40 by 10, 40, 50, 60, 20, 28, 28 by 10, 2.8, 24 plus 2.8 is 26.8. 26.8 should be the bicarbonate, but the bicarbonate is 21, so it is 21, 27. Difference is like 6 or 7, so the acceptable range is plus minus 2, so it is more than that. So there is not just compensation, but the bicarbonate is extra low. So extra low bicarbonate means the secondary disorder is a metabolic disorder, and as bicarbonate is a alkali, it is low, that means the acidosis, the secondary disorder is acidosis, a metabolic acidosis. So as this is a metabolic acidosis, we should calculate the anion gap. The anion gap is 140 minus chloride is 99 minus bicarbonate is 21, which is 90, 100, 110, 120, 20. The anion gap is 20, but again there is given that albumin is 2, so the corrected anion gap is 20 plus 2.5 into 4 minus albumin. Albumin is 2, 4 minus 2 is 2, 2 into 2.5 is 5, 20 plus 5 is 25, so corrected anion gap is 25. So this metabolic acidosis is a high anion gap metabolic acidosis. So in a case of high anion gap metabolic acidosis, we should calculate the delta ratio. The delta ratio is delta anion gap by delta bicarbonate. Delta anion gap is 25 minus normal anion gap is 12 by delta bicarbonate. Normal bicarbonate is 24 minus here bicarbonate is 21, which means 12, 13, 13 by 3, which is 13 by 3, nearly equal to 4. So whatever be the high anion gap metabolic acidosis, the delta ratio is high, because it is the maximum case it can be 2, not 4. So if it is 4, there is another disorder present. So if the delta ratio is high, that means that delta anion gap by delta bicarbonate is high, that means delta bicarbonate is low, that means the bicarbonate is high. So the bicarbonate is high, that means that the secondary disorder is metabolic, and the bicarbonate is alkali, it is rising, so metabolic alkalosis. So the disorders here are a metabolic alkalosis, a high anion gap metabolic acidosis, and a acute respiratory acidosis. So three disorders in this patient is going on. So what can be happening in this patient? Like I can assume that the high anion gap metabolic acidosis may be from the alcoholic ketoacidosis or maybe lactic acidosis. The acute respiratory acidosis is because high alcohol consumption, the respiratory center got depressed and the patient is hypoventilating, and the metabolic alkalosis may be due to the vomiting, the GI acid loss. Now let's get to the last question. In the last question, there is a patient on metformin, the patient has fever, the patient has diarrhea. Whenever I am in this kind of question, I am getting the history of metformin. We know that metformin is a risk factor for lactic acidosis, so we are keeping this in mind. Now pH is 7.2, which is low, that means acidosis. PaCO2 28, low, that means metabolic acidosis, as both are in same direction low. Now what we should do, the compensation is 2.5 not 2.5, 1.5 into bicarbonate is 13 plus 8, 13, 7, 7, 13, 14, 15, 16, 17, 18, 19, 20, 20, 20, 19, 19.5 plus 8, 19 plus 8 equal to, and it's equal by 26, 27.5. So this should be the PaCO2 value. The PaCO2 value is 28, 27.5, close enough, so it is compensated, adequately compensated metabolic acidosis. So let's calculate the anion gap. The anion gap is 130 sodium minus chloride is 97 minus bicarbonate is 13, 97, 13, 90, 10, 100, 7, 10, 110, 130 minus 110, 20 equal to 20. The anion gap is 20, so it is high anion gap metabolic acidosis. If the anion gap is high, we should calculate delta ratio, which is delta anion gap by delta bicarbonate. Delta anion gap is 20 minus normal anion gap is 12 by delta bicarbonate, which is 24 normal minus here it is 13 equal to 8 by 11. So it is nearly, if 8 by 10, 0.8, less than 0.8. So the delta ratio is less than 0.8. So if we are suspecting a high anion gap metabolic acidosis, that is lactic acidosis, and so that in case lactic acidosis, the delta ratio is normally in 1 to 2 range. So the delta ratio is abnormally low. So how this can be low? That means that the delta bicarbonate is high. The delta bicarbonate is high means the bicarbonate is more less. So bicarbonate is less, being less. So by the disorder will, and the extra disorder will be a metabolic disorder, and the bicarbonate is being less, so bicarbonate is alkali, so it will be metabolic acidosis. So the secondary disorder present here will be a normal anion gap metabolic acidosis. So in this case there is a high anion gap metabolic acidosis coexisting with a normal anion gap metabolic acidosis. So what should be the high anion gap metabolic acidosis? Maybe lactic acidosis, and the normal anion gap metabolic acidosis may be due to the GI diarrhea, due to diarrhea, the GI loss of bicarbonate ions. So this is it for today. Thank you.